Let me welcome everybody to, I can't remember which number this is, 8th or 9th of our ECS and cloud feedback virtual symposiums. My name is Andy Dessler. I'm one of the organizers, and I'm just going to go over some of the general ground rules before I turn it over. So today's presentation will be a little different than the ones we've done in the past, where we've just had sort of people giving talks like an AGU session. This is actually more of an integrated event. We're going to have 2 AGU style talks on a subject of great interest to the community, I think, about high climate sensitivity, how reasonable that is. And then hopefully our hope is that we have lots of discussion following it, people asking questions, making comments, arguing with people. I believe everyone should be muted automatically and not be able to unmute themselves, although I'm not 100% sure if that's the case. But in any event, if you have questions or comments, you're welcome to type them into the chat at any time. If you prefer to actually ask the question live, raise your hands and we will unmute you. So the organizers will sort of go through and run this like a Q&A session. And so hopefully we'll have lots of good discussion. And let me just finally end by saying we now have a newly constituted executive committee for this. Nick Letzko, Jonah Block-Johnson, Sheely, myself, and Christy Prosescu. And so if anybody has any ideas, wants to volunteer to give a talk or anything like that, you're welcome to contact any of us. We're always looking for ideas of interesting things to do. And let me finally last say, I think Christy's not here, but congratulations to Christy. I was typing on Slack with him and literally every other word was a typo. So I'm pretty sure he's tired. So I don't know if he's watching or not, but well done. And we will look forward to having you back soon. Anyway, with that, I will turn it over to Nick.
Yeah, thanks, Andy. And I guess thanks everyone for being here, and also thanks to Kyle and Thorsten for putting themselves out here to have this conversation. As Andy said, we're going to have 2 talks of about 10 to 15 minutes. Thorsten Mauritsen is an associate professor of climate science at the University of Stockholm, and he's going to be making a case that we can rule out an ECS of greater than 5 degrees. And then Kyle is also an associate professor at the University of Washington, and he's going to try to make a case that we can't quite rule that out yet. And so with that, Thorsten, could you get started?
You got to unmute yourself. We can see it.
Thank you. Good, you can see it. So basically here I was given a mission impossible. Of course, you can't really rule that out. So together with Kyle, I sort of changed the question a little bit, that by ruling out climate sensitivities above 5 degrees, we really mean it's less than 5% probability. So what IPCC would call extremely unlikely of being true. And so I'm going to try and make the case that we can already do that by now. And so I'm going to assume that everybody here knows what ECS is. It's equilibrium climate sensitivity. And also that people are broadly familiar with the WCRP assessment on climate sensitivity, but I'll just talk very briefly about it. So it all started back in 2015 when a bunch of us met in this beautiful venue, including me and Kyle, and talked about climate sensitivity and a bunch of other things. And after that, we started a process. I forget how many co-authors there is, but 25, 30 people were involved in this, and it went along 3 lines of evidence. So we collected all the evidence we could from process understanding, historical warming, and paleoclimates, and then we used a statistical framework by James and Ann, where you combine all that information into an estimate of climate sensitivity. And so this really breaks a 40-year scientific deadlock. And so you can see over here, I plotted the WCRP assessment and compare that to AR5. We're basically halving the uncertainty since then. And so in the baseline estimate, which is the one I plotted here, the 95th percentile is at 4.7 degrees, so it's already below 5. So I'm done. But the devil is really in the detail, and people will argue, no, you can choose a different prior, or there might be some dependencies between these 3 lines of evidence. So the 95th percentile could still be above 5 degrees. And so for the sake of argument today here, we will argue that WCRP says it's maybe 5 or 10% probability. So my task would be to halven that. Okay, and so the way I'll go about that is that I will show you some new in the press observational estimates of low cloud feedbacks that improve the process constraint. That alone will be enough to fulfill my mission impossible. But I will also talk about other things. And so one of the things that I think the WCRP assessment misses is to use the temporal evolution of historical warming. And I will also talk about 2 recent studies that show that pattern effects are potentially overestimated. And finally, I'll show you some plots of CMIP6 models that we're very fortunate to have, several of them with climate sensitivities above 5 degrees, which are inconsistent, showing inconsistent behavior with past climate change. So this is my argument. Now I could have done many other things, but I think these are the more convincing ones. And so first, new estimates of low cloud feedback. So this is Tim Meyer's paper, which is in press, and he kindly let me show his results here. But there's also another one that came out recently, Susanna and Delgenio, and there's an LES study by Jule Radke and co-authors that came out last year, which supports this. And so basically what Tim Myers did was that they looked at observations of clouds from satellites and looked at how they respond to meteorological conditions, and then they project that on global warming to get near global estimates of low cloud feedback. And so what's really new here is that tropical convective clouds, so cumulus, trade cumulus, or tropical ascent region cumulus, are near 0 feedback, whereas models tend to have positive feedback from these clouds. On the other hand, you have a stronger positive feedback from stratocumulus and also slightly more positive from mid-latitudes. But in the end, they end up with a narrower range of uncertainty here. And so what they actually did here was they ran it through the WCRP code, which you can do. So you can download the WCRP code, make a new estimate, and see how that impacts. And so it has fairly little influence on the peak distribution here. It moves the percentiles by a few tenths of a degree, but really what's important here is that you have the probability that ECS is above 5 degrees. So they say it's 3% here. So that's one. Then the other thing, which I think is a missed opportunity, and Kyle will argue the opposite, but basically the historical warming estimates is giving us no information regarding ECS above 5 degrees. And you can see this from this plot here, where you can compare the black, so the baseline PDF, with the orange, where you remove historical information. And although things change over here, there's no change in the PDF above 5 degrees. So I'm asking myself, is this a missed opportunity? To understand why I think that is the case, you must first understand what is done. And so basically you take 2 periods and you average the temperature change. You come up with estimates of the forcing change and the imbalance change, and then you end up with a PDF of ECS. So this is an example from a few years back. And this is actually, I think, an interesting story for the audience here. Is a few years ago, these types of estimates were based on HACRU-T data, AF5-based forcings, and this imbalance change, and there was no pattern effects being taken into account. And so those types of studies ended up with best estimates of ECS of 1.5 to 2 degrees, and some PDF distribution, which is fairly skewed around that. And so this was a big challenge, I think, for the community. And so what has happened is that in each of these 4, so to say, inputs, people have been looking at what could be biased in these estimates. And so in each of them, things have changed so that ECS became higher. And so there's been corrections for incomplete coverage, fair enough. Surface air versus surface temperature, people have looked at models. There's a weaker overall forcing change due to more aerosol cooling. People have found more changes in heat content. And note here that the uncertainty estimates are actually not overlapping. And we've included pattern effects based on AMIP experiments. And so you end up with an essentially unbounded distribution from historical warming. And so what you can see in CMIP6 models, which is plotted here on average, the red line, is that throughout this 50 or 60 year period, they're basically not, they're basically colder than observed on average. And so the way that can happen is that you have too much aerosol cooling, and see some of the models are even cooling here despite global warming. And this can happen because you kind of have different evolutions in the greenhouse gas forcing, which continues upward here. Aerosol forcing compensates some of that out to here, but then there's not much change afterwards. So you can imagine that within one model you can have uncertainty in the aerosol forcing level, and so you can have near compensation in this period, but then afterwards you can have warming here. And so the average from CMIP6 models is about -1 watts per meter squared aerosol cooling. And yet they are not warming enough. And so in the WCRP assessment, we're assuming a median of 1.2 almost, and a whopping range from 0.37 to over 3 watts per meter squared. So basically canceling all greenhouse gas forcing. And so we know the world is warming, and we know the world warmed by a sizable amount even here at mid-century. So we can rule out most of that aerosol forcing distribution here. And so that basically diminishes all probability that ECS is above 5. Now, in a moment, Kyle will argue, or on the flip side, I should say. On the flip side, you can also look at warming after this period. So in this period where you don't have much of a change in aerosol forcing, so models can compensate. And so in this period, and this is from Femke-Neis's paper, in this period, these high ECS CMIP6 models are basically not consistent with the observed warming. So on the flip side, I said, Kyle will argue that pattern effects could, make up for the aerosols. And so pattern effects, unlike aerosols, won't really show up in the temperature record, like we just argued. And so forced temporary SST patterns like these in this figure here may act to dampen global warming, and so can disguise a given ECS with a lower TCR. So a high equilibrium climate sensitivity model can have or reality can have a lower transient warming than what you might expect if there weren't these pattern effects. And so also natural variability can cause such patterns. In the observational record, we cannot really distinguish forced from variability patterns. Oh, I don't know why I wrote that. Anyway, so early estimates were based on AMIP2 experiments. And so basically you take a model, you expose it to observed SSTs, and you don't give it any forcing. And then you can estimate a feedback parameter here. And what we see here is that in all of these models, this is from Andrews et al. 2018, in all of these models, the feedback parameter in the AMIP experiment is much more negative than the feedback parameter that you get from 4 times CO2. So we followed up on this and looked at one of these models, so ACAM6, which is kind of mid-range here. And we now, sign conventions are the opposite. We compared these AMIP2 based experiments with another data set and found a much weaker feedback here. The feedback that we got in the HAD-ISST based experiment is consistent with what the corresponding coupled model would do in the historical experiment. So it's still a pattern effect, and the feedback is still more negative than what you get in 4 times CO2, but it's what you would expect from that coupled model. We confirmed this with CAM5 Green's functions, and an independent study by Chen Xu found the same thing. So what do we make of this? Well, we are not really there yet. We're working on it. All we have is, 2 different clocks. We don't know what the time is then. And so one of the potential problems with the AMIP2 dataset is that it's really concatenated from 2 different sources. And so once you're looking at trends over periods crossing this concatenation time, you can potentially get biases. And so that's where I think the issue is. And you can basically see that before 1980, you're getting very similar results, and after 1980 or 81 or whenever it was, you're getting different results. So finally, I would like to show you some results from more CMIP6 models. And so these are all paleoclimate experiments. Unfortunately, there's only one model which has really dared to publish these results, and that's the CESM2, which has a 512 Kelvin climate sensitivity. Would be really nice to see more models, but basically this is the Pliocene, a period slightly warmer than today, where this model is outside what you would expect. You have the Eocene, which is far back in time, much warmer, and basically the CESM2 is again outside what you would expect. And for the last glacial maximum, which is not so long ago, it basically cools to very low temperature, much lower than what we think is reasonable. So I would say that the low-level cloud feedback on its own is enough for me to fulfill my mission. I would also say that probably temporal evolution of historical warming is enough, and in particular, it's enough if we can bound pattern effects better, and I think we can, but maybe we are not quite there yet. And then I kind of showed you auxiliary evidence. Of course, you could imagine that you could create some model that would, perform on all of these indices that we saw, but so far we haven't seen a high ECS model emerge that can do historical or any of the paleoclimate cases. And so therefore, I think it is extremely unlikely that ECS is larger than 5.
Awesome. Thanks, Thorsten. This is a great presentation. There's one quick clarification question in the chat, which was about the color symbols in the Myers et al. Plot. Steve Klein responded that the blue markers were satellite data and the orange red markers were CMAP5 and CMAP6 models.
Yeah.
I think the label is cut off.
Oh, sorry. Yeah.
Yeah.
This is what happens when you do this quickly. So these are observational estimates. These are models.
Great.
Is that right? Yeah.
Yeah. Okay, thanks. Kyle, do you want to present your rebuttal?
Yeah, sure. Although I'm nervous that it's not going to be as convincing. That was a great presentation, Thorsten. Yeah, can you hear me okay, Nick? All good? Okay, thanks so much. So yeah, that was a fantastic introduction to this question, and a nice introduction to the WCRP report. So I'm going to kind of take all that as background information. And like Thorsten, I'm going to kind of make the point up front that I don't think we can really definitively rule out something like greater than 5C. And so I'm going to also kind of take the approach of questioning what the probability is about ECS greater than 5C. And just to keep in mind, right, a 5% chance is a 1 in 20 chance of something happening. And that can still be an uncomfortable possibility, even if we can confidently say we have only a 5% chance of something. So I'm going to be trying to answer these questions of what's the probability of ECS greater than 5C? And the other question is, should we really discount models that have an ECS that's above that value? And like Thorsten, I'm going to kind of start with the WCRP assessment, Sherwood, Webb et al. 2020. And their headline estimate was that ECS is probably about 3 degrees with a 17 to 18% range of about 2.6 to 3.9, and then they gave this 5 to 95% range of 2.3 to 4.7. And if you crunch their numbers, you get something like a 3% chance as the kind of headline estimate of being greater than 5 degrees. Just a quick note that I'm going to be talking about ECS here. What they actually estimated in the paper is something called the effective climate sensitivity, which they termed S. But for all intents and purposes, they're almost identical. So let's just call it ECS. And the issue really comes to a head when you look at the climate sensitivity from models. So I've done some research here and searched Twitter for the best histogram of ECS coming from Gavin Schmidt. I think the calculations are from Mark Zelinka, but I like this figure just because it really shows the issue. We have the pack of models here, we have the Russians, and then we have the wolf pack, the high ECS models. And something like, I think 7 or 8 models are above 5 degrees or something like that here. I forget the exact number, but it's more than 3% of the models. And so the real question is, what do we do with that information? Do we discount those models, or is there really an inconsistency between our estimate of the probability of being above 5 degrees and the number of models that are actually in that range? And I think there is, but it maybe isn't quite as bad as that 3% implies. And so I just have a few key points that I think will maybe not fully convince you, but I think hopefully seed some doubt in your mind about how well we actually know that upper bound. So the first one is that if you take a look at the Sherwood, Webb et al. Result, there's a ton of good information in that paper about sensitivity tests. And I think the team of authors did a really good job of thinking about all the different possibilities of how the range will be affected if you drop out certain lines of evidence or if you test priors. This is just an example here where the choice of prior matters quite a bit for the upper bound. And so if you take a look at the headline statement in the paper, what we're really using there is a uniform feedback or uniform lambda prior. And what that means, kind of illustrated down here, is uniform probability in lambda, which actually implies this very, very skewed probability in ECS. And so the prior itself very much favors low ECS and very much disfavors high ECS. And that's part of the reason that you're able to achieve a fairly strong constraint on the upper bound. If you instead use a uniform ECS prior, or uniform S here, it's the same thing, that's this orange line. If you assume basically uniform prior in ECS itself, then you end up with this red curve over here, which basically doesn't change the lower bound, the 5% confidence interval, but it does change the upper bound. So you go from something like a 3% probability of being above 5 degrees to something like a 10% probability of being above 5 degrees just from these different choices of prior alone. And so I don't know what the right prior is. I think these are really nice bounds of kind of reasonable choices. But the point here is that the upper bound is pretty fragile. Subtle changes in choice of prior or how much you weight different lines of evidence, or the connections between different lines of evidence that you might have to account for. All of these things tend to affect the upper bound much, much more than the lower bound. And so I think that's just an inherent asymmetry that we have to kind of acknowledge, that the upper bound is going to be inherently more fragile. And it just means that it's very hard to talk about what the probability really is at the upper bound. The difference between 3% and 10% above 5 degrees comes down to these kind of relatively subtle subjective choices in a lot of ways. And so if you take that, that uniform ECS prior, suddenly that upper bound jumps up to something like 5.7, close to 6 degrees, and therefore quite a larger probability of being above 5. So that's just an example. The paper does a whole bunch of other really nice sensitivity tests. For instance, dropping out different lines of evidence. So you can throw out the historical evidence, you can throw out different periods from paleoclimate. So for instance, if you drop all of paleoclimate, you jump up to something above 6 degrees as the upper bound. That is the 95% confidence interval. The point I want to make here is to check out the lower bound. In all of these cases, you're pretty much not changing the lower bound very much at all. And so this is another illustration of just how much more confidence we can have in the lower bound compared to the upper bound of ECS. Another key point is that paleoclimate's doing a lot of the heavy lifting here, at least in the WCRP paper, where if you toss out the paleoclimate lines of evidence, that affects the upper bound of ECS much more strongly than, for instance, dropping out process evidence, which is our knowledge of climate feedback processes, or tossing out the historical evidence based on the observed historical warming. And so this, I think, is really interesting because there's so much exciting new understanding coming out of the paleoclimate community. So on the left here is just a highlight of a paper recently by Jess Tierney and group, kind of reassessing the magnitude of global cooling at the LGM. And using interesting new methods, including data assimilation, so taking priors from coupled models and combining them with proxies to produce new estimates of the spatial pattern and global mean temperature change at the LGM. And they, in that paper, argue for slightly more cooling than we thought previously, so a slightly higher climate sensitivity. So that's an example of what I see as kind of a fast-moving and really interesting field that's informing our understanding of paleoclimate. But at the same time, it's somewhat disconcerting that paleoclimate is kind of providing such a strong constraint on the upper bound, precisely because we're not sure to what degree these past climates are good analogs for the future. And so this is an example from Jian Xu, also working with Jess Tierney, looking at, for instance, consecutive doublings, or I think they did 1, 3, and 6 times CO2 in a couple different models, and showing how the effective climate sensitivity varies across climate state. And it increases strongly in, I think this is CAM5, and I think this blue line is CAM4. It does not increase very strongly in CAM4. So depending on which model you choose, you get different estimates for how climate feedbacks vary with climate state. And we need to know this in detail if we want to use these past climate states to infer something about near-term future warming. And the issue really is quite critically dependent on how things like cloud feedbacks and water vapor feedbacks will vary across climate state. And so I just point this out to say that if we want to use these paleoclimates to really constrain future warming, we really have to have a robust understanding of the physics behind how these feedbacks change with the state. And in the WCRP paper, Sherwood et al., we did think a lot about how these feedbacks might change, and we used a wide range of feedback changes with a large uncertainty to kind of account for lots of possibilities. And so that's kind of built into the uncertainty in that paper. But I think it's still an open question as to what nature actually does in this regard. So I still personally have a bit of worry about the confidence we can put in LGM or Pliocene type constraints because of these feedback changes. So that's kind of key point number 2. And then key point number 3 is that Thorsten talked a lot about emergent constraints as kind of an additional line of evidence that we could bring in on top of the WCRP result. And so I just want to say just quickly that I think there's a lot of emergent constraints that are looking very promising, but others have proved to not really hold up under, say, the change from CMIP5 to CMIP6. Still others are missing underlying mechanisms, which should reduce our confidence. And then the thing I want to talk about here quickly is that there could also be biases in emergent constraints that kind of trick us into thinking that there's more confidence in them than there really are. And so overall, I think this is another fast-moving field that's relatively new, really just the last 5 years or so, and caution is needed in our interpretation of these emergent constraints. And so here's an example of how they work. These blue dots here are hypothetically different GCMs from CMIP5 or CMIP6. If you can make an observational, if you can find a correlation between some observational metric and the true ECS in these models, and you can make an observational constraint on that, whatever metric you're interested in, then you can go up to this line and kind of read off what we think nature's ECS is. It's not a problem if there are just errors in the models. If they kind of go in random directions, all you do is water down that emergent constraint, you make it slightly more uncertain. But the problem arises if there's a common bias. If all the models kind of have a common bias, or they are all missing some physical process, you can shift them all in one direction or the other with respect to whatever emergent constraint you're interested in. And then you can make a measure of that observation, and then you might infer a climate sensitivity, which is either high or low compared to the true climate sensitivity, if there's this shared bias. And so I just want to show one example of where I think there might be. And so this is the nice paper that Thorsten mentioned. Really fantastic work. These authors, I think, have really pushed the field forward in thinking about emergent constraints based on the recent warming of the last 40 years. But this is exactly the kind of period where I think there actually is a shared bias in the models. And so this is just a quick summary of some work that by Cristi Poisescu. I'm working on with him and Yue Dong and a bunch of other authors. What we're really interested in is whether there's an emergent constraint bias coming from this period, precisely because the coupled models at right fail to replicate the observed SST pattern since about 1979. And note that this period, since 1979, is not really sensitive to data set like Thorsten is talking about since the 1800s. This is a pretty robust pattern across all the data sets that we've looked at. And so the issue here is really that there's been cooling in the East Pacific and cooling in the Southern Ocean, whereas the models show slightly less warming in those regions, but certainly not cooling on average. And in fact, no models really replicate both the cooling in the East Pacific and Southern Ocean at the same time. And the reason this matters for the rate of warming is that it projects onto things like the estimated inversion strength and cloud cover. And so we've seen in reanalysis products a strong increase in EIS in regions like the East Pacific, and a growth of low clouds there. And so a reflection of more sunlight over this period of time, and a slower warming, presumably because of that a cooling effect of additional clouds. And that's not true in the coupled models at right. Basically, no models get close to seeing the EIS changes that we see in reanalysis products. However, if you take the same, if you take the exact same atmosphere models, at least those that are available, and run them on top of the observed SSTs, then you do produce the EIS changes and the cloud cover changes. And so the implication here is that part of the reason that the coupled models may be warming too much on average since 1979 is simply because they don't get the right pattern of warming over that period. And we think that pattern of warming has encouraged the growth of low clouds and slowed the global temperature change. And so this is the kind of shared common bias that might influence those emergent constraints. And so this is just very much work in progress, but here's an example, again, from Cristi, where you take all these historical simulations of models, you find this correlation between the warming rate, and then you can observe the warming rate and infer a low ECS. But if you take a subset of those models that allow you to do this calculation, what he's done here is basically said, if you, instead of using the coupled model feedback values, you instead estimate what the warming would have been if you use the AMIP estimated feedback pattern, it shifts the warming rate to the left, and all of them are more consistent with the observed rate of warming. So this is one way to do it, is basically just say, assume the ocean heat uptake efficiency stays the same, and ask what the warming would be if you just replace the feedbacks with AMIP feedbacks, given the right, conditioned on the right SST pattern. You can also do this with large ensembles. If you composite on those large ensembles that have SSTs that are closest to the observations, that also shifts things to the left. And you can also do this with energy balance models. So you can take the two-layer held model, for instance, and run it with different feedback patterns based on the AMIP period. And that also shifts things to the left. And so the point here is that the observed warming is probably not enough to tell you that high ECS models have an ECS which is too high, because they would have simulated slower global warming had they had the right pattern of warming over that period. And it's still an open research question as to why models fail to do that. It could be internal variability, or it could be a problem with the physics or the forcing within those models. And so that's kind of open research that I think is a really important question to answer. But for now, I would say I think this kind of emergent constraint, we should just be cautious about it, because I don't think we know the answer to the degree to which this really constrains things. And then finally, emergent constraints from paleo are really interesting. Thorsten showed this figure, and you can put emergent constraints based on the Pliocene. But here, I think there are still open questions about whether SST patterns matter for this period as well. So this is just an example, a kind of model-based reconstruction from Natalie Burles, suggesting the Pliocene SST patterns look like this, which looks quite a bit different from what we've observed in the recent 100 years, and also quite a bit different from where we think we're going in the future. In particular, it looks like the Pliocene had a lot less warming in the Western Pacific. And this would be the kind of thing that would favor very high sensitivity. And so it raises a question of whether the models get this pattern right during the Pliocene, and if they don't, how this affects the emergent constraint from that period. And raises, I think, another question about if this is the pattern of warming we can expect in the future, this would favor very high sensitivity, even higher than what the models predict. If they were to simulate this pattern, it would basically enhance the feedbacks toward a more positive value and higher sensitivity. And so I think all these are kind of open questions, which in my mind make it difficult to say what the probability of greater than 5 degrees is. So these are kind of my conclusions. I think in round numbers, the Sherwood Webb result, the ECS is about 2 to 5 degrees. That's a good estimate, but we should have less confidence in the upper end because it's more fragile than the lower end. And I would argue that even 2 to 6 might be defensible. And so I personally think that more work's needed before we can declare victory here. That I think greater than 5% chance of being above 5 degrees is still possible. In contrast, I think the lower bound is much more robust. The realism of ECS values in models can't be assessed by just comparing to these ECS values from assessments like this. I think you really need process level and like with like comparisons to be made. So for example, we need to ask the question whether the cloud properties, the models that have improved cloud properties, for instance, in mixed phase clouds in the mid latitudes, do those tend to be more accurate or less accurate compared to observations? And do those tend to come with higher or lower ECS? And so that's an open question, I think. And overall, I would say it's just a really good thing that we have models that span the full range of ECS. And we should have been more worried that CMIP5 models didn't span the AR5 ECS range. They're useful for thinking about kind of low probability, high impact futures. And they're also a critical component of emergent constraints to have that spread. So I'll stop there, and I'm looking forward to the discussion. Thanks, everyone.
Awesome. Thanks, Kyle. That was great. There's a lot going on in the chat. So Jonah and I will be monitoring it. I guess the first question that came up from Maria was, she says, when I look at the histogram, it seems a bimodal PDF is a better fit. Please comment. So I guess that's asking in the WCRP assessment, what happens if you use a bimodal prior, something that looks kind of like the distribution, the raw distribution of ECS values in the CMIP6 models.
Sorry, is the question about the histogram from WCRP or histogram of the CMIP6 models themselves?
I think the question is, if you use the histogram from the CMIP6 models themselves as the prior, and then follow the WCRP procedure, how does that affect things?
Oh, I'm not sure. I haven't thought about that before. So using the CMIP6, so I haven't read the chat yet, so I'm scanning up for the question.
Okay.
But I don't know. I'm not sure. Using the CMIP6 models as the prior, that would give you a bimodal distribution. I don't know. Thorsten, do you want to comment? Or maybe Maria, is that what your question was? I'm not sure if you can unmute. And...
Yeah, more or less, but it was even simpler than that, because the red histogram did not look like the PDF to the left, but maybe it's not the same thing. And excuse my ignorance, ECS assessments, I don't have too much knowledge of that.
Yes, I think you may be talking about this slide.
Yeah.
Yeah, so the histogram at right is just the raw CMIP6 model ECS values, and the PDF at left is based on the WCRP assessment, which did not use those raw values at all. It's coming from all the 3 lines of evidence that Thorsten talked about. It's just a different choice of prior that is not informed by the model ECS. So they don't have to look like one another. But I was raising the point that the fact that they don't look like one another is perhaps an issue. If we have too many models with high ECS, it's a question of how do we deal with that model ensemble if they're kind of too weighted toward high values of ECS. And I don't have the answer for that, but that's kind of, I think, the point of the discussion today is what to make of that information. Yeah.
Thank you.
Mm-hmm.
Jonah, do you want to take the next question?
Sure. Robert Wood asked, what do we know currently about the aerosol forcing in the LGM? How that might affect our use of it as a constraint on sensitivity? I think there was some addressing. Andres said more dust in the LGM caused more aerosol forcing, but it's quite uncertain. Maybe around 0 to 1 watt per square meter. Does that fit with the panelists' understanding, or?
Thorsten, do you have a number on hand for that?
I mean, I'm not a very strong on paleo, but you can see in ice and other records that there's more dust generally in cold climates, and so one of the ideas is that that could have caused some of the cooling, and so I think that's what they are talking about here. And so I guess one question is how many of the models included this, for example, as you're looking at emergent constraints. But it's something like that is included in the WCRP assessment, as far as I remember. But I don't know the numbers.
No, just say if anybody in the audience knows, chime in.
Just to piggyback on that question, do people have a sense of that uncertainty when it comes to the higher ECS? I mean higher CO2 paleoclimate proxy? Or is that just a source of uncertainty that is hard to?
I mean, maybe I can say something quickly here, which is I think this is a key issue for how we interpret things like the LGM. So if we have a model that cools too much during the LGM, it could be cooling too much because its ECS is too high, or it could be cooling too much because the forcings are wrong. And I think it's very hard to tell the difference between those two cases, or it could become combination. And so if you have a model which starts to cool too much and then all of a sudden the sea ice feedbacks explode and it runs away to some kind of very cold state, that's some combination of perhaps too high ECS and too large aerosol forcing or ice sheet forcing, for instance. And so I think these are, I think, where the open research questions are, and part of the reason that I think caution is needed for things like emergent constraints coming from the LGM and Pliocene is because you really need to have a handle on all of these non-CO2 forcings before you can claim that it's really the modern day ECS which is causing a model to be too sensitive during those periods. I think we can possibly do that still from those periods, but I think that's still just a thing I'm cautious about personally.
Okay, there's quite a lot of discussion in the chat about paleo, but I may want to ask this question from Maria Rugenstein, who asked, what about the temperature dependence of feedbacks? So actually, Jonah recently showed that these effects can kick in at around 3 or 4 degrees of warming, independent of the pattern effect. And so obviously, if we have temperature dependent feedbacks, that could dramatically increase ECS independent of any historically observed warming. So maybe Thorsten, could you comment on that?
Sure.
Is that something you worry about at all?
I think about it. I hope I don't have to worry about it. Yeah, sure. I mean, this has been an issue, and it's a particular issue because we typically use 4 times CO2 rather than 2 times CO2, and we define ECS with 2. And so many of the models run over 3 or 4 degrees in those experiments that we use to probe the ECS. On the other hand, we don't run them to equilibrium. So there's been, like, at least in my mind, a trade-off of about 10% errors from these 2 effects, but we have maybe not so much constraint on the state dependency. Although what you can do is you can look at the paleoclimates going further back in time, and there you are well above this temperature, and so it doesn't seem that the proxies would support a really dramatic state dependency there. That's my take on that. But sure, something we think about. Yeah.
Kyle, do you have any thoughts?
Just to say it's something I definitely worry about. I framed it kind of in the context of paleo. If we want to use these paleo periods, you have to know something about that transfer function of how feedbacks will change. But I think you're right. Your work, Jonah, just suggesting that even just going forward from modern day, if there are slight nonlinearities in the feedbacks, that can lead to large uncertainty in that tail. And that's an additional thing I didn't kind of have time to mention, but I'm with you on that. I think I do worry about those kind of things. And I don't think the paleoclimate record gives us enough accuracy to really nail down those mechanisms at the level we need to rule out that possibility, even though I agree with Thorsten that I think it does hint that warmer states have higher sensitivity, colder states have lower sensitivity, and it seems consistent with our understanding in that. But really we're talking about the details here of how fat that tail is in ECS, and for that, even slight uncertainties can really change the answer.
And I'm sure.
Maybe I can just add on top of that, if there is such state dependency, that means ECS estimates based on these warm states is overestimating. So that's going to give you a high bound on ECS when you're thinking about warming from pre-industrial up to 2 times pre-industrial CO2 levels. So it actually works for limiting the upper bound on ECS. But of course, it's worrying if we continue to warm the Earth that we kind of push it beyond these linear regimes. Of course, that's what I meant about worry.
Yeah, can I ask a quick question about ECS? So when you're looking at the paleo data, are you really looking? You're not looking at just the fast feedbacks. You're looking at really Earth system sensitivity. So to what extent does that mean that this paleo really aren't good? Good comparisons for the problem of modern climate change? It's something that's always bugged me. So what do you guys think about that?
That has been considered in the paleoclimate, in the estimates from the paleoclimate. The difference between Earth system feedbacks and fast feedbacks has been considered.
Yeah, that's right. The WCRP paper has a correction factor for going from Earth system feedbacks to fast feedbacks. So it's treated slightly differently for the LGM and for the Pliocene estimates, but those things are accounted for. But I would say that's an additional kind of area where there's some uncertainty, right? I don't think we know with high confidence how you go from Earth system to fast feedbacks, and so you have to basically treat that as an unknown parameter and add some uncertainty to it, which is exactly what the Sherwood Webb result has included.
All right, it looks like somebody has their hand up. Thomas, do you want to unmute yourself?
Yeah, thanks. Nice talks and really interesting. But I want to add perhaps a little to the controversy by asking the 2 speakers the question, if the effect of the warming pattern is as large as Kyle's estimations suggest, and if we cannot actually determine a single value for the climate sensitivity of AMIP runs based on forced SST runs, pretty much regardless of those SSTs are really, because we are in principle looking at the property of the system that does not depend on those SSTs, or at least not on the fine details of those SSTs. So I keep wondering, and I have been wondering for 20 years, honestly, how well defined, how well posed is the question of climate sensitivity based on a global mean average surface temperature? Are we able to give a unique answer to this question, or are we actually looking at an ill-defined question?
So I guess you're referring to what Kyle was showing in the end with the patterns from Pliocene, right?
Yes, yes, but also your note.
So my take is a bit different than Kyle's, is that we're getting those patterns in the Pliocene because reality has different feedbacks than what models have. And so if you expose a climate model to those SST patterns, that's going to be incompatible with the climate feedbacks that they have. And it's going to show up and give you weird results, basically. That's my own personal take on that and where I would go with that. I'm unsure how you would somehow have some magical forcing in the Pliocene that would give you such strong polar amplification without cloud feedbacks, essentially, or some other feedbacks. I have a hard time understanding that. So that's my take on that.
I can add something just on that Pliocene point. The figure I showed from Natalie Burrell's work, I think that's a nice figure just for illustrating the issue, that if it's true that that was the Pliocene pattern, then we have a lot of work to do to figure out what that means for ECS. Recent work by Jess Tierney suggests that pattern isn't quite that extreme. Maybe it's closer to what the 4 times CO2 model patterns of warming look like. And so I think there's active work in that area that may resolve some of these things. But I do think that the Pliocene may turn out to be one of our strongest constraints, because if it was a pattern of warming that looks a little bit more like that, it was favoring high sensitivity during that state with very positive low cloud feedbacks, for instance, and it didn't warm so much more than the modern day. And so that may end up being a very strong constraint when you account for that warming pattern. At the end of the day, I think the Pliocene may still be the hero for constraining the high end. But more generally, your question was, how useful is the concept of ECS? And for that, I think it's still a useful concept. However, you have to when you're talking about things like whether it's 5% or 10% probability above 5 degrees, you have to get into the weeds and start thinking about these details. And that's where the SST patterns matter, and how you combine the different lines of evidence and the choices of prior, all of that stuff. And so I guess part of my argument is there are subjective choices and active research in all of these areas, making that a very hard thing to quantify. But I still think it's a very useful concept just because it gives you the bulk global temperature estimate going forward, and it correlates highly with future warming. And so I don't think we should abandon it, but it's a good thing that we're having these arguments now about these little details as opposed to order of magnitude estimates, I'd say.
Yeah, I was going to say it's amazing how far the field has come. Let's see, more questions?
I think
Yeah.
Ben
Ben Sanderson had his, Ben Sanderson had his hand up for a moment.
Oh, hey, yeah. So great talk. This has been a fantastic discussion. A couple of questions, which I've kind of had since the WCRPO report, really, about the independence of different, the independence of the model which we construct, which is represented as the statistical model, which was in the WCRP assessment. So, firstly, the way that the pattern effect is treated as a different thing. It's the different parameter in the paleo constraint as it is in the constraint relating to recent warming. Whereas you would expect there would be some sort of those things shouldn't be purely independent. The physical properties of the pattern effect responses in the paleo evidence have some relationship to the recent evidence, but also in the way that we define the processes, the construct of having the effective climate sensitivity, the Gregory climate sensitivity, which rolls in together to some degree, some feedbacks on different timescales. We're sort of assuming, and then we have another parameter representing the error in that due to the pattern effect. But you could construct it in a different space. You could construct it as knowledge of short timescale feedbacks and slow timescale feedbacks, and that might be more physically plausible. That might be a more physically intuitive way to think about it, because there are physical feedbacks which relate specifically to different timescales and specifically to different patterns of warming. And if the problem was framed having those physical processes as orthogonal, would you get a different answer? And I don't know the answer to this question. I'm putting it out there.
Sorry, I'm not sure I quite followed. Do you want to say something, Kyle?
I think I understand the question. There are multiple ways you can frame the same problem. The feedbacks can change with state or time. And one way we chose to do it in WCRP report is to think about the feedbacks can shift with SST pattern. They can also shift with global temperature. They can shift whether you include Earth system feedbacks or fast feedbacks. So we kind of treated those all as piecemeal. We had corrections for each of those things, and then we kind of treated them independently. And then you're saying at the end of the day, we combine them. I think what you're looking for is some kind of broader theory that says feedbacks can change on a range of timescales and states. And you could have a theory written down for the fact that we've only observed the very fast feedbacks in the historical record, for instance, and we haven't yet seen the emergence of feedbacks associated with Southern Ocean and East Pacific warming, for instance, right? It would be really nice to have that full theory. So I would love that. I don't know how to do it.
No, I mean that's the point. I mean, So the wider question is like, does the answer depend on the way that you frame your degrees of uncertainty? I guess you could summarize it like that.
It certainly could, I think.
Or have we baked in some independence between the parameters by framing it as ECS plus pattern effect?
Yeah, I'd have to think more about that.
Yeah. Actually, I think Yue Dong's paper gets at that, doesn't it, Kyle? You guys was that most of the spread in ECS due to the feedbacks over the fast feedbacks, basically?
Yeah, that's right. So her 2020 paper suggests that just in terms of understanding the CMIP6 spread, it doesn't seem to be coming from pattern effects in terms of why the models have a larger spread in ECS. It seems like it's coming from the fast time scale. So it really is atmospheric physics as opposed to pattern effects. I'm not sure that's fully answering your question, though, Ben. That's a slightly different thing.
I think the CNRM model is the exception to that, and that one shines out in the recent TCR in the TCR constraints because it gets the recent warming right, but it still has a high climate sensitivity. So I agree, the general trend is right, but there are exceptions.
Maybe I can just add one more thing here, which is I think the field has kind of gone in the direction of thinking about pattern effects as a feedback change. You could imagine a different formulation. I think people have suggested this. I think we actually argued about this for the WCRP report. You could imagine representing it as some additional forcing associated with the SST pattern, for instance. And mathematically, I think it works out to be the same thing. You can say you have some temporary forcing associated with the SST pattern, which then goes away when the SSTs change. That is mathematically equivalent to having a feedback change. But I'm not actually sure how that would interact with all the other lines of evidence. And so I imagine there could be some work to be done about how the formulation actually influences the final answer. So I guess I'm agreeing with you, Ben. I think it's worth thinking about, but I don't have an answer for how that would change the final output of that.
Cheers, Kyle. Thanks.
Okay. Isaac Held makes a point in the chat that we have to be careful what we wish for. A low sensitivity world with a large specific pattern effect will presumably have much more dramatic precipitation changes in the tropics and stronger changes in stationary waves propagating into mid-latitudes. I think also gets at the question of maybe there's other ways of getting at the pattern effect, for example, looking at precipitation. And I guess I kind of wanted to probe you guys both on this question of the historical pattern effect. It seems like, at least my takeaway is Thorsten thinks there could be, the historical pattern effect could be purely forced, or it could also reflect some internal variability. And if it's more forced, then that probably points to a lower ECS. And if it's more internal variability, then it's a higher ECS, or a higher ECS is plausible. Whereas Kyle, it seems like you're just saying the models get the historical pattern effect completely wrong. Or at least there's some evidence for that. Is that the right way of framing it?
I guess so. I prepared a slide, if I may.
Uh-oh, I didn't prepare a slide.
Prepared a slide for you. If it wants to. So we've had a lot of discussion around this potential bias and pattern effect from the most recent warming, and so one of the ideas that that are out there is that could be some kind of natural variability that created this pattern effect, and that may go away very soon. And so it would trick us into thinking that the climate sensitivity is low, but really we're going to see very fast warming in the future. Now, if you look in this paper by Chris Hederman at 15,000 years of historical simulations, and you look for aliases, so that is 15-year periods where the warming is much less than expected, you're going to find that there's absolutely no relationship with pattern effects measured from the top of the atmosphere radiation budget. So basically, there's no connection, no statistical relationship in this model, admittedly, between things you measure at the top of the atmosphere in terms of imbalance anomalies and anomalies in the temperature trend. And so my interpretation of these results is that basically you're seeing a strong anti-correlation between anomalies in the radiation budget at the top of the atmosphere and at the bottom of the mixed layer, so here measured at 100-meter depth. And so you can interpret this as these natural variability TOA anomalies. Really what they do is they tap into the deep ocean. They don't get their heat from the surface temperature. And so basically the relationship between, say, anomalies in the top of the atmosphere component. Oh my God. It doesn't like that plot. It has too many dots. Okay. Oh, it got stuck. Anyway, I think that there's not much relationship between natural variability, pattern effects, and temperature trends. I do think there's a relationship with forced pattern effects and temperature trends. That's what I wanted to say. Okay. Sorry for screwing that up.
Yeah, this is where I think we have a really different interpretation. I do think the internal variability since 1979 can play a big role in temperature trends. And I can dig up some figures if people are curious. Maybe I don't want to show them because we're almost out of time. But if you look at large ensembles and you ask which members of the large ensembles warm by more than others, it is related to the SST patterns in those ensemble members. And this is work that Christie's kind of working on finalizing and writing up now, except that he just had a baby, so maybe it'll be another 18 years before he gets it out. So I think it's not quite as simple as the energy just goes into the deeper ocean or something. It does look like there's a correlation between SST patterns and feedbacks over the historical record and the rate of warming, which is part of our argument for why that emergent constraint needs some caution, I'd say.
We should probably say that we're at an hour, so if people need to drop off, obviously people can quit a Zoom call anytime they want, but maybe the official end will be here. And if Thorsten and Kyle want to stick around for a few minutes, I find this interesting. We can keep talking, but just say thanks to everybody who showed up. It's a very interesting discussion, and thanks to Thorsten and Kyle for some really terrific presentations. So we'll stick around if anyone else wants to, but otherwise have a good day.
Yeah, happy to stick around, but thanks everybody.
Thank you.
Bye.
Pretty soon it's just going to be the wind whistling through the trees and us.
Challenging to try to read the chat and keep track of the conversation. There's so many good points in here. I loved it.
Yeah, I have to say this is one of the places where Zoom is fine for giving a presentation. I think it's not as good for discussion because there are too many things going on. It's kind of hard to have, it's hard to have a real organic conversation, but you do the best you can.
Yeah, I might try to save the chat and either post it somewhere or post a summary. There's a lot of really interesting discussion about the paleo work.
Yeah, the chat it'll save. You record the talk, it saves the chat.
Okay.
So the chat will automatically be saved. Yeah.
Well, happy to take other questions in person. Well,
yeah,
unmute yourself.
People can unmute themselves if they want to ask questions.
when
Well,
it
maybe
does.
there are no other questions. People are ECS'd out.
Hey,
All right.
Mark.
Oh, hi.
Oh, good, Mark.
This is. Oh, hi. Hi. Yeah. So just a comment about the discussion about potential dependencies between. I think Ben was arguing that there could be a pattern effect dependency between the paleo and the historical evidence. So we did do a calculation in the assessment, a simple model calculation looking for dependencies between pattern effects in between the historical and the process evidence, and it actually turned out the effect was quite small. James and Anne did have an explanation for this. It was something to do with the fact that the actual shared variance was small. But another thing, we have the baseline range, and we also have our robust range, and the robust range was based on what happens if we knock the various lines of evidence out in turn. So, for instance, we remove the paleo evidence and we remove the historical evidence, and so if there was if, for instance, you were over constraining because you weren't taking into account a relationship between the historical and the paleo, then knocking one of those lines of evidence out would then remove that. So that was one of the motivations we had for doing these robustness tests where we knock things out in turn. So I just thought I would comment that was part of our thinking, and that's catered for in the assessment. That's one of the reasons why we have this robust range, and we argue that the baseline range on its own may be overconfident.
Yeah. Thanks, Mark. That's
Sure.
great.
Thank you for that.
That's why I also said up to 10% rather than the baseline case 3% risk of ECS being above 5. That included that. But on the other hand, I think it's pretty unreasonable to say that there's 100% dependency between two of these lines of evidence. I think that's a gross overestimate of dependencies. And so that's what you do when you throw out one of the lines of evidence.
Yeah, so what we were trying to do with those robustness tests was put bounds on, and of course they are generous.
Yeah.
Yeah, that's also kind of why I focused on the prior. I think that's in my mind where there's a little bit more subjectivity there. Throwing out an entire line of evidence was a great robustness test, but at the end of the day, our robust range was up to about 5.7, which is basically what the shift in the prior gave you anyway. And so I thought that was a decent approximation for kind of the uncertainty. So I agree with you, Thorsten, like 5 to 10% was a fair assessment of what we said in that paper. But yeah, thank you, Mark. That was good. Good point.
So another point was that it's been mentioned by a number of people that we didn't use the time variation of the historical data, and obviously there have been studies which have constrained the aerosol forcing based on that, as Thorsten mentioned. So again, we did have a reason for not including that, which we did state in the paper, which was that we weren't confident that if we included that information as well as the endpoints, we wouldn't be, double counting in some sense. So we were, Steve and I were concerned that we might introduce an element of double counting and hence over constrain if we did that. So that's why we left that out. But I guess it would be possible to sort of formally explore whether that information that is added, whether there is unique information in there when you add in. We just couldn't think of a way to do that formally at the time. So, I mean, I agree that's a useful area for further work.
Casey Wall has had his hand up for a while. Casey.
Hi, thanks, Thorsten and Kyle. Great talks. I just have a question about the role for deep convective cloud feedbacks in this discussion. And I was interested in, Thorsten really highlighted the Myers et al. Paper, which is, I think, really awesome work. And but I just don't think we have something equivalent to that for deep convective cloud feedbacks in terms of process understanding and observational constraints. So I was wondering if the field advances in that area, how much that might impact the estimates of ECS. In other words, if we can constrain from observations deep convective cloud feedbacks, how much influence will that have on our understanding of high ECS probabilities?
I think it would have a similar order of magnitude impact. I think we are estimating the annual area feedback to be something like 0.2 plus and minus 0.2. So of similar magnitude to the low cloud feedback in terms of uncertainty. And so if we could constrain that, that would be valuable. I didn't really bring that up because people tend to think that it's controversial and so on. So I just stuck with what the WCRP assessment said. And I think that if there was a study, and I guess you're working on that, that would constrain these types of cloud feedbacks, that would be valuable for sure.
Steve Klein or Mark Zelinka, do either of you want to comment on that? I think you're the experts here. I wouldn't have anything to add beyond what Thorsten said.
Steve wrote something.
Yeah,
I think Steve answered in the chat, but
great.
Yeah, you could go through the same analysis that we did in Myers. It would definitely affect the the process level PDF to some extent, but then, as you then combine it with all the other lines of evidence, it kind of gets watered down in terms of what it can actually do in the final posterior ECS PDF. So, you'd have to run it through the entire Bayesian calculation to find out exactly what it would do for the final ECS distribution, but certainly that is the area in the process level that has the largest uncertainty among all of the cloud feedback. So it would be very valuable for that line of evidence to further constrain the high cloud feedback.
Yeah, I think also there's this asymmetry between the high and the low end in terms of the impact of uncertainties in these little feedbacks. And so I think you're going to see, like I showed in the plot from Tim Myers, is you see small changes in the middle of the distribution, but it really has an important impact on the tail, on the high tail. So valuable, yes.
Sounds good. Thanks.
Please, Steve.
Right, we probably ought to start. We probably ought to start wrapping up. It's almost quarter past. But again, thanks everybody. We're recording this. We'll put a recording of it up. And in fact, if the chat looks sufficiently interesting, maybe we can archive that also on the website. But anyway, thanks Thorsten and Kyle. I really appreciate it. It was really good discussion and good to see both of you guys.
Yeah, good to see everyone. Thank you so much for having us.
See everyone, yeah.
thanks a lot, guys.
All right.
Thank you, guys.
And bye, Christy. Get some sleep.
Oh yeah, Christy is online. He's just
Christy is online.
Congratulations, Christy.
This is the only way you get out of changing diapers. All right. Bye, everybody.